too much communication. Anyway, so let's continue our journey in the land of particles on surfaces of circles and spheres to essentially hydrogen atom eventually. And last time I introduced angular momentum, the components, and like consideration in different system of coordinates. So let me just quickly review that it will be useful for us to be familiar with the operators which here, where do we start? Operator of angular momentum, because kinetic energy for particle on a ring will be written as square of angular momentum divided by 2 masses and the radius squared, right? So, and then this angular momentum operator, it's the definition is pretty much you take the classical one, right? And it has 3 components related to the right-hand rule of cross product of r vector with the p vector, and then you, in order to go to the quantum mechanics, you just substitute a momentum operator by its quantum representation as a derivative with respect to a certain component, right? And then you have these 3 components, 3 operators. Now you can square them, sum. This is what we call square of angular momentum operator. And what do we know about commutation relations of these components and L square? Do you remember anything from previous lecture? Yeah.
L squared means with each of the
That's right.
but they don't commute with one another.
Yeah, that's correct. You know, I usually actually increase the number, like whatever points you get in the exam, I add extra if you participate in class. So, for example, this gentleman, he got 1 point on the midterm just because he is answering questions and asking them, right? Just to be clear about procedures. Now, you're exactly right. You have we have these commutation relations between the angular momentum components. They're easily derivable from just the basic definition of what the components are. And L square is this magical operator that commutes with everything, all components, not everything. And we also talked, because different components do not commute with each other, then we can only with certainty define one component and L square, because these 2 operators will always commute. Now, which component? Usually, for historical reasons, people choose LZ. There is no really any rationale to prefer LZ versus LX or LY, right? But once we've chosen one component, then there are these pictures that usually are drawn, and the meaning of this picture is that you can have, what does it mean that to have a vector of that represents operator? Operator is not a number, and vector is usually, what is it? Like if we have a 2-dimensional vector, usually to draw the arrow of a certain length and a certain direction, you need to have numbers, right? So then you can draw an arrow. But if you have an operator there, dx, and this one is dy, how would you represent this vector? So these arrows kind of don't mean much if you just consider operators, but what they actually mean is that operator, L operator, for example, it has 3 components, Lx, Ly, and Lz, and then every component can be turned into a number if you average it with the wave function, right? So then, if you average every operator component with the wave function, you get, this is a number, 5, 6, 7. So that's how these arrows originate. Now, why do we have kind of a certain value of Lz? because we are taking the wave function, which is an eigenfunction of Lz here. And that means if it's eigenfunction, then it should have eigenvalue. Let's call it Lz small, and then psi, presumably normalized. Then you get Lz, which is just one number, and that's kind of the height of this projection of that arrow, right? Now, why do we have the circle here? Huh? I was explained last time. Yeah, that's right. It's in an xy plane. But why do we have a circle instead of, or multiple arrows all have the same projection in Lz, but definitely different values of x and y? Why do we have that uncertainty? Anyone in the back row? Who doesn't commute? Yeah, they don't commute. But why do we draw a circle instead of a one particular point on that circle? Yeah. What does that mean?
Well, the Lx and My operators don't commute, as you said.
Yeah.
And
Sure.
Because they don't commute, therefore, they won't have the same eigenvalue for the.
Different operators can have different eigenvalues, even if they commute.
They won't have the same eigenfunction, which means we can't know the x and y arguments with certainty.
So let's say if you have an operator A, right, and another operator will be whatever A. I guess pi if we add plus 5. Okay, so then if we have a function f and it has eigenvalue 3f, then this guy, if we apply that to the same function f, what we will have? We have af plus 5f, which is 3f plus 5f, 8f, right? So definitely, do these operators commute? Huh?
Yeah, they do.
They do, right? So if you add any constant to any operator, you get new operator that commutes with the previous one, right? But definitely, as you can see from this simple exercise, the eigenvalue here of a plus 5 is 8, and for the function which had eigenvalue 3 for function f, right, for the operator a. So that is a simple example where two operators commute, but they have different eigenvalues. So if operators do not commute, they can have different eigenvalues. They can have, well, if you have a function, what is important, that function cannot be eigenfunction for both of them if they don't commute. Okay? It's about eigenfunction, not about eigenvalues. Eigenvalues are, well, they're just numbers, some numbers. And certainty is not related to the fact that eigenvalue is of certain value, right? Certainty or uncertainty is related to whether you can make function of your system, wave function of your system psi, be an eigenfunction of two operators at the same time. And it's impossible if operators do not commute. Now, Lz doesn't commute with Lx or Ly, so that means if we have our system, which is an eigenfunction of Lz, so that means we have a clear one number for a, like, I don't know what function this is, but all I know is that it's an eigenfunction of Lz. So it has a certain value of Lz. Now, it cannot be eigenfunction of Lx or Ly. That's why if you measure Lx or Ly on the same eigenfunction of Lz, you will get all sorts of values, right? That's why these values are represented as a circle. Can be anything, okay? Now, the length of the vector is well defined. Why? Because length of the vector kind of we established in order to get the vector we need to have an average with the wave function. Then you will get the components of the vector, which is Lx averaged, Ly averaged, Lz averaged. All right, and this will be certain. This will be some numbers. And then the length of the vector, if you measure the length of the vector, then it's Lx square plus Ly squared plus Lz squared. Okay? And taking the square root of that. Now, is that what L square is or not? So what I'm asking essentially, is this equal to L square averaged and taken square root of? Because there are two different ways to go about length of the vector for the operator. You can average operator that has three components with a wave function. For every component you take the average. You square those averages and you take sum of them and take a square root, right? So that's like from this point where you obtain the essentially vector of three numbers, the length of the vector is defined like by this expression. Now you can go about this differently. You can consider the operator squared, take an average, and then take a square root of that average. Right, so that's the second route. This is the first one, and this is the second. My question is, are they exactly the same or they are different? Yeah.
Different?
Oh, they're seemingly different. But it's interesting to establish actually whether they are the same or not. They are different because you have, well, formally they are different because you have L square here, and wave function presumably is taken as an eigenfunction of both Lz and L square. Right, so that value is equal to L plus 1 times the normalization, and we want square roots. Right. Well, this is something where we actually need to calculate these guys. They are not. They will be different depending on the wave function, right? So we cannot say exactly what the sum of the two. Well, without additional algebra, at least. So it's a good exercise actually to see how different these two. I cannot answer right now on the spot, but you potentially can, with the different with slightly more algebraic expressions, derive what this will be and how does this x square root compare to this square root, because formally they are different square roots. Here you have an expression of the operator which is an operator for eigenoperator for this function, right? And the eigenvalue is defined, while here only Lz square is an eigenoperator for the wave function that we start considering. Okay, so this is about angular momentum. Let's get back, and there are spherical coordinates that you can go into and define what L square is. Now, why do we want to do that? We want to do that because this expression of L square, so just to remind you, particle on a sphere, that's the problem we are considering, right? It has Hamiltonian that is essentially kinetic energy, right? And then kinetic energy of the particle on the sphere is related to L squared divided by 2mr squared, right? So r is kept constant, so all we need is to find eigenfunctions for L squared. Okay? And if we can find eigenfunctions for L squared, then we solve the problem for particle on a sphere, Hamiltonian. Okay? So that's why we are looking for the simplest possible expression for L squared, because we don't want to work with something difficult. Now, it turns out if you look at the coordinate expression of L squared in Cartesian coordinates, it's more complicated than this thing. Okay? You can write down the Cartesian easily because you know all the components, right? And you know how to multiply operators, that sort of stuff. So obtaining this expression is a little bit harder. It's done in these notes in so-called appendix, where essentially you practice the chain rule. We practiced that when we were looking for the expression for kinetic energy in two-dimensional case. This is a three-dimensional case. Even more lengthy discussion is going on, and eventually I'm not going to go through it. You know the chain rule, and you can do that at home if you'd like. The idea here is essentially that we arrive to the expression of L squared, which looks like this. Looks somewhat intimidating, but in reality it turns out it's actually quite simple, much better than the Cartesian expression. Now, what is this? This is our Hamiltonian times wave function equals energy wave function. So it's essentially our time-independent Schrödinger equation for particle on a sphere, right? And now we will be looking for energy in this form, and the constant will be our eigenvalue for L squared, right? Now all we need is to find eigenvalues and eigenfunctions for L squared operator, and it's done in the following fashion. It turns out that this complicated looking operator contains just two parts. If you focus on the angles, right? So there is this complicated derivative with respect to theta, right? So we call it a theta. And then we have this operator, b theta. But the simplicity of this operator is that it's just a function of theta, right? It's a multiplicative. We don't differentiate with respect to theta, so b is somewhat simple. It will commute with another function of theta. Now, in this operator, there's only one part where phi is involved. It's a second derivative, right? And it turns out it's just Lz squared, because Lz component in the spherical coordinates is just minus I d over d phi. Okay? So then squaring this expression, that means it's a second derivative, minus I times minus I. It's minus 1, and that minus 1 is just taken outside. So we can write L squared as this expression. Okay? Now, we're looking for the solution of this eigenvalue problem, and it turns out we can write down the eigenfunction as a product of some function of phi times some function of chi. All right? Why is that? Well, the secret here is, although this part doesn't commute with that part, and it seems like it's not a separable problem, so the separable Hamiltonian would be having a theta plus c of phi, right? So that would be simple. But it turns out that having a form like this is also easy, because what we can do, we can write this product form, and then, yeah, so one function is fixed to be an eigenfunction of Lz. And what happens when we apply L squared to the product? A doesn't act on the phi function, right? Only acts on the chi, so it leaves phi alone. Now, in this case, in the second part, Lz action on phi is very simple. It just brings the m squared because it's an eigenfunction. Chi is acted upon by B, and so we don't know what this is, but we can just keep it like that. What is important is that both sides, or like both parts essentially, they have phi function that can be taken outside and then cancelled from the expression of the eigenvalue problem, right? So you can see that phi can be taken away outside of the brackets here, and here it's just a product form. So we can cancel phi, and what we have at the end is an equation for chi that depends on m. That's the only part that was taken for whatever function phi we decided to put in the product. That's the only trace of that function through the eigenvalue of this problem, right? So is this simple? Well, the equation itself may be not simple, but what this operator, why am I stating this repeatedly, that this operator is relatively simple? Because it allows us to split the problem with 2 degrees of freedom, 2 variables, into 2 problems that are not anymore coupled or anymore depend on each other significantly, only through this number m. But then we can solve them separately, essentially. Any one-dimensional differential equation can be solved by variational approach relatively easily, no matter how complicated well, the operators are. You can kind of represent this chi function as some linear combination of other functions and turn this into an algebraic problem. So this problem, if you write what A and B's are, and we wrote them, right? So this problem can be solved exactly, but I'm not going to go into the solution, like details of how this is solved. I'll just announce what the result is, okay? And we start with the eigenvalues. L squared times equals constant times function. Constant is an eigenvalue. And that eigenvalue is equal to the following form. It is h bar squared L times L plus 1. And that's the same L that you encountered already in general chemistry when they talked about s, p, d, f orbitals, right, in hydrogen atom. Then this L, S corresponds to L equals 0, P corresponds to L equals 1, D to 2, F to 3, and so on and so forth. Those are essentially numbers corresponding to the angular momentum numbers, right? And then the length of the vector, as I wrote here, if you take a square root, it's L times L plus 1, and you need to take a square root of that to define the vector, because this norm is usually 1, right? And now the functions themselves, the ones that you also saw in general chemistry, this S is a spherical function, P is like a dumbbell shape. These are encoded in the so-called spherical harmonics. Those are eigenfunctions of this problem, okay? And they, as we saw, this L squared problem depends both on M and L. Then the functions also have 2 indices, M and L. M defines which function of angular momentum projection you are taking. And that also a particle on a ring problem, eigenfunctions. And these Y functions are corresponding functions of theta, the second angle. That's the equation that I didn't go into in details, But yeah, these are solutions. They are well known, tabulated, and yeah, essentially accessible in literature. Now, the interesting relation between L and M is that whatever L you pick, M can go only up to plus minus L. Okay, so and that relation you also remember probably from general chemistry, that S well, has only M equals 0, P, right, P orbitals, they have 0 and plus minus 1, or X, Y, Z components. And then if you go to D, then they have 5 components. And we will talk about them in a moment. Now, there is a small discrepancy between what I will be talking, well, like if we just look at these functions and what you saw in general chemistry, because in general chemistry people prefer to work with real functions. These functions are complex. They have this exponent of I phi. Those are the complex functions, right? But we'll see that this this problem can be easily removed if you rotate within the subspace of degenerate functions. Now, the spectrum, how does it look like? It looks like this, which is like essentially going by well, going from S orbital to P orbitals and D orbitals. So here the energy of S, P, and D are different, while in the hydrogen atom we will see that actually energies of S, P, and D, they all can be the same, and they don't depend on L. But that will be a slightly different story. Now, for the particle on a sphere, energies of depending on L will be changing, but they don't change depending on the M, because the energy expression is just depends on L, not on M. Okay, so M enumerates the functions which are degenerate within the with this energy layer, essentially, right? So the situation is that for particle on the ring we had dependence on M. When we went to the 3 dimensions, we have eigenfunctions which are different depending on M and L, but energies are constant and independent of M. They only dependent on L, the angular quantum number. Okay? Yeah.
What do the numbers on the vertical axis?
Vertical axis, those are essentially the same, well, these energies in the units of, well, the coefficient is just to put, this is the unit of those numbers. So 2 would correspond to 2 times h bar squared divided by 2 mu r squared in absolute values, right? So this is just to have integer numbers instead of some constant that is not even yet defined, because mass will depend on the mass of the particle, radius will depend on how big is the sphere, right? Okay, so one interesting classical analogy which you may notice or may not notice is that if we just say rotate within the subspace of xy, right, in classical physics, so like in the figure skating, for example, there is this way the figure skaters increase the velocity of their rotation, right? How do they do that? They pull the hands closer to themselves. So in physics, what does that mean? In physics of this expression, if we think about numerator and denominator, right? So if we are in xy plane, if we don't move and change our xy coordinate, they don't do that, right? They don't change the z coordinate. They only are kind of concerned about the angular velocity in xy plane, right? So they want to increase their angular momentum. That's how fast they're rotating. Now for that, in order to, well, they have some kinetic energy to start with, and to increase the L square, if kinetic energy is conserved, then you need to reduce this, right? Do you know what this quantity is? Yeah. Moment of inertia, right. So how do they reduce moment of inertia? By pulling the hands together. Why does it reduce moment of inertia? It reduces the radius, keeps the mass constant, but essentially, what does radius correspond to if you are dealing with a human body?
Like, I get the center from the distance from the center.
Yeah, but it's a human body, right? So distance to what? Yeah.
The center of mass. You bring your hands in the center of mass.
But you cannot. Center of mass is 1 point, right? Which is somewhere inside you, right? So how do you bring the center? So it's just, I guess what I'm confusing you with is trying to apply the physics of one particle or single particle, right, to the solid body essentially, right? And if you have here we are working with even like in classical limit of this expression, we are working for the particle, right? And the particle doesn't have a size. It's my mathematical kind of physicists work with particles, and in classical physics those are idealized essentially points which do not have size. Now if you try to apply this to a body or like some continuous object which has shape, then you need to formulate moment of inertia as a essentially integral over the space, and then there will be mass distribution, right? And then there will be distance essentially from the center of mass. Let's say if we put the center of mass at 0, then there will be kind of r squared, that means x squared plus y squared plus z squared, right? So we need to take this integral in order to define what the moment of inertia is, integrating over the whole body, right? Now when they bring hands together, they just change the distribution function of the mass. Mass is distributed so that you put more mass outside in the regions where you are farther from the center of mass. When you bring it together, you're not bringing all the mass to the center of mass, but rather you are making the distribution of mass in space more localized, closer to the center of mass, and that reduces the moment of inertia, right? So that with the constant kinetic energy, that will definitely increase your angular velocity. You can try it at home. Right, it's really easy. Even if you are not with skates, you can just rotate and just bring them together, and they will rotate faster. Okay. Now this is a classical analogy. The quantum case is somewhat. That's actually quite interesting thing that in quantum mechanics, when we are talking about eigenstates, they don't move anywhere. Right, so the probability density of stationary states is they are not dependent on time, right? And what does kinetic energy mean in this case? In classical physics, the faster you moving around the center of mass or some point, center essentially of your coordinate system, the higher the kinetic energy, because your angular momentum is higher, right? Faster you rotate, and the higher the kinetic energy. Now, in the quantum world, you are working with eigenstates; they don't move anywhere. What is this? How do we think about the kinetic energy? Kinetic energy corresponds to some. Usually, in classical mechanics, corresponds to some movement. Here, there is no movement. Right? Where did how did energy present itself? You may think in quantum mechanics, the kinetic energy. How do we see it? Well, we already saw for a particle in the box, it's the number of wiggles, right? But in the angular momentum case, it's about rotating around the axis, right? So although nothing is actually moving, but the symmetry of, say, the easiest case is a particle on a circle. We saw that wave functions phi m is 1 over 2 pi exponent of plus minus I m phi. So, well, let's just make it simple, I m phi. And then the kinetic energy was Lz squared divided by 2 mr squared, right? So then you just have h bar squared, m squared, 2 okay, so m, let's put n instead, because then it will interfere with our mass definition. All right, so this is our energy, eigenvalues, this is our kinetic energy operator, right? These are our functions. And if we plot real parts of these functions or complex parts of these functions, then we will notice that, say, if we start with n equals 0, then the picture will be like you have a circle, and n equals 0, that has just a real part. The whole function will be symmetric, right? Plus or minus in the circle, right? It will be 1 over square root of 2 pi. Right? Constant value. Now if we put n equals 1, what's gonna happen is that we're gonna, well, on the circle, that's our kind of, that's the place where the particle is, and the function will look like with one node. So essentially it will be positive here, negative here, right? And if you have n equals 2, then we'll have a circle with more than one node. So somewhere here there will be negative value. Yeah, so it's something like positive here, negative here, positive here. So on and so forth. You have more nodes essentially when you go around the circle. And those nodes, like particle in the box nodes, it's just here there is more to it, and that's related to the kind of rotational property of the wave function. And yes, we'll discuss that when we start talking about spin. But essentially, there is some symmetrical property of the function that symmetrical with respect to what happens when we rotate the system of a coordinate, and how the function will change when we rotate the system of the coordinate. So that will be important for the spin. But for now, let's just move on and see what's gonna be. Okay, so this is just a summary of the L square and LZ operators that they commute. That's why they can have eigenfunctions of simultaneous eigenfunctions. And these are eigenfunctions, these are eigenvalues. The eigenvalues for the LZ is related to M. Eigenvalues related to L square, they were related to L value, L times L plus 1. And here again the relation between the same kind of diagram as we saw before, that the length of the vector is always defined and the projection is always defined, and depending on the projection we can have such distribution of vectors. So what does this all mean is that if we say pick some particular spherical harmonic function Lm with certain L sets up the M range between 0 plus minus 1 plus minus 2 and up to plus minus L, right? So how many values of m 1L allows you to have? 2L plus 1. Right? So that means for if L is fixed, we have 2m plus 1 functions. And for all these functions, every function here, the case where L equals 2, the d orbital essentially was considered. And you have 5 vectors that are built using the 5 functions like this, with L equals 2 and m ranging between -2 to 2, right? And so all these vectors, they essentially build out of the components of angular momentum. And their length is defined and the projection is defined. Okay. Now, the picture of this visualization spherical harmonics, we have 2 angles. How do we visualize these functions? What usually is done is we take points on the surface that have the same value of the function, so isosurfaces. Like we in the lab, you probably already plotted the orbitals, right? So the orbitals are plotted in the same way. If you have 3 coordinates x, y, z, and also you need a coordinate for the function, right? How do you do the plotting? Well, you fix one coordinate, right? So the radial coordinate is fixed, and then you see how what should be the spherical coordinates, that or angle coordinates that keep the essentially the probability density value the same on top of the shape that you are plotting, right? So the constant probability density plots, and here they are. Okay, so S orbital looks like an S orbital, right? Then P orbitals, they look differently than what you may expect it, because well, this PZ type of orbital looks like PZ, but these guys, kind of analogs of PX and PY, they are well, just two degenerate bubbles essentially, torus. And then with L equals D, L equals 2, you have 3, because there is a kind of shape degeneracy in here and here. And F also look differently than you would expect from course of general chemistry. And the reason for that is because we have simply complex orbitals, these y functions, they are complex. And what we plot in general chemistry is different. These are real combinations. Now, how do we make real combinations? Using the earlier expression, we notice that, okay, we have kind of this one, say, y1, 1 and y1 minus 1. They look like with the different just exponential factors. You can add them together or subtract, because these complex exponents are there with different sign. Then you end up with cosine phi instead of the complex exponents of I phi, right? And the same here, you can subtract them and divide by I and generate essentially sine function instead of cosine. And these combinations will be completely, well, real now. They won't contain any i's in them. And that's what usually is plotted when we talk about spherical harmonics in general chemistry. All right, we'll see that if we want to go to the hydrogen atom, then this angular dependence will stay. That's why kind of it's beneficial to study it, even though we keep right now the radius constant. This is just the angular part. And what did we see in terms of energy? Energies of all these orbitals, right, within the same L, they are the same, right? So we can easily mix eigenfunctions, and that will still kind of be the same kind of eigenvalue for the Hamiltonian, for the energy, right? If your two eigenfunctions have the same eigenvalues, you can mix them freely, and you will get the same eigenvalues again.
So is that like hybridization?
No, it's not hybridization, because in hybridization, well, maybe it is somewhat like hybridization, because but in terms of, say, hydrogenic atom, where you have one electron and just nucleus, and if you consider hybridization as, like, say, sp3, so s and p orbitals, they have all the same energy, because energy in a hydrogen atom depends on n, the principal quantum number, right? So you can easily mix s and p. But when do we talk about hybridization? We talk about hybridization when we consider, say, carbon, non-hydrogen atoms. There, s, p, d, all these orbitals, they have different energy. So when you mix them, you get something completely mixed up, essentially. Like, it's not going to be eigenstate of any Hamiltonian. That's the problem with rigorous introducing of hybridization, is that it's not like the orbital that you obtain. It looks like what is generally taught in these courses of general chemistry, but it is not an eigenfunction of any Hamiltonian, right? So from quantum perspective, it is something, some superposition, essentially, right? So here, what I'm talking about is I'm mixing eigenstates with the same eigenvalues. By eigenvalues, right? I mean eigenenergies, because energy, where is the energy expression?
It depends on the principle.
In this case, energy depends on the L square, right? L square, it's L, essentially, times L plus 1. So L square is the same, and the radius is fixed, mass is fixed, so the kinetic energy is the same for both of these functions, right? You can potentially mix all of them within the same L. I'm not mixing functions with different L's, right? I'm mixing some function within the same L, so they have the same eigenenergy and even the same L square eigenvalue. So therefore, whatever I obtain, it's still an eigenfunction. Okay. All right. Any more questions? Because we're running out of time. So we solved today, or at least discussed the solution of particle on a sphere, right? And to do that, as you may have noticed, we use the fact that the L square operator, right, contained Lz squared, right? So the general part when we were discussing the solution of L square, right, here, we had Lz squared, and that helped us to formulate the solution of this equation, spherical harmonics, as a product of two functions. One is an eigenfunction of Lz, and Lz we already saw for particle on the rim. Therefore, we kind of used we solved the two-dimensional problem in previous lecture. Now we kind of, with the help of the two-dimensional problem, we solved the three-dimensional problem on the sphere. Although it was a quasi-three-dimensional because we fixed radius. Although it was on a sphere, but in reality we had only two angles, right? So it's quasi-three-dimensional. But next lecture, on Monday, we will address hydrogen atom, so we will release constraint on the r, on the radius. And it turns out that the Hamiltonian we'll get when we consider hydrogen atom in the spherical coordinates will contain L square. So we will use pretty much the same trick. We already know the solution for L square. We will put the total solution as a product of solution for L square times the radial part, and we will formulate by the same algebraic technique one-dimensional equation for the radial part, and we won't solve it as today. So I will just talk about the solutions. All right, and we will see the nodes that, you know, that 1s function doesn't have a node, 2s function has one node, 3s function has two nodes. There's some nodes that they sometimes talk in general chemistry or in organic chemistry, right? So that when you go by principal number, you have radial nodes and maxima and minima of the probability density. Okay, and we will also talk about how to define the size of atom, right? Which would be, yeah, you will see. It will be kind of how much density do we have in the certain radius, right? So that's how one can possibly define. Although it's just one way to define what's the radius of atom is. Okay. Okay. So I'll see you on Monday. All right.